Now recording. Let's see if we can get this. Yeah, now we're recording, finally. Okay, let me get the last couple of announcements in. First, I wish more people were here. We've already lost one that was there. Student course evaluations are now open. They've been open, I think, for a little bit. So what that means is, are all of you familiar with doing student course evaluations? Okay, go on there. Do the student course evaluations. They are very valuable to us as instructors. To me as a department chair, this is how I help evaluate my instructors that I don't get to see teach every day. I find out from the students what they think of them. We also, in addition to the courses and the instructors, you also are asked generally to evaluate one or two other things, like registration procedures, library, food services, something like that, maintenance, So if you are requested to do one of those, please do those as well. We get to interact with you 2 or 3 times a week, okay? So I get some feedback that way. Those folks, they don't have all that opportunity to feedback, so that's the best way they know of whether they're doing their jobs well or not. So please let them know. All right, any questions? The other thing is anyone who's graduating this term, they have been given, they did yesterday, I don't know if it's still going on today, the CAP exam. Or any of you graduating? You took it yesterday, okay? And Michelle's here, okay. So I'll probably repeat again about student course evaluations late in the class, but I did want to get it out there now. All right, any questions on anything we've done up till now? We're in Chapter 2, which is Polynomial and Rational Functions, 2.6, which is the rational function part. And I think we got through example 4, and we're ready to do example 5. However, it's not on the PowerPoint, so I was going to use the example 3 slide here because it has some white space on it. This thing is so slow today. I punch something and nothing happens, and I punch it again, and then the first punch comes through. Okay. This one, example 5, sketch the graph of f of x is equal to x over x squared minus x minus 2. Okay. So sketch the graph. That's all it says. I want to know what you think the first thing we ought to do in order to sketch that graph. Second? Okay, find the values that the denominator can, well, that the variable in the denominator can't be, and what would that be? Okay, the denominator cannot equal 0, so I'm going to put x squared minus x minus 2 cannot equal 0. Then what do you do with that? Okay, how do you do that? Factor, okay? Now, how does x squared minus x minus 2 factor? X minus 2, x plus 1. Everybody see that? Real easy to check it, FOIL it. X times x is x squared, plus x minus 2x would be minus x minus 2. Got it. And that cannot equal 0. Where do you go from there? So each one of them not equal to 0, x minus 2 cannot equal 0, and x plus 1 cannot equal 0. Because if either one of them were 0, then your denominator would be 0. What does the first one give you? X cannot equal number 2, and the second one, x cannot equal negative 1. Now, how does that help you in your graph? Those things, okay? The vertical asymptotes, those identify your vertical asymptotes. So I'm going to go ahead and start on my graph. Sorry, it's going to be sort of messy. And here, Amber Jones is here. Okay, And by the way, congratulations to those of you who were recognized on the Honors and Awards Day. Others, I think, will be coming in who also, others were participating, like Amber Reese. She was a ambassador, and the ambassador is quite well in the competition too. So, all right, we'll tick off a few data points here, not too evenly spread, but you get the general idea. All right. Now, how do we indicate x cannot equal 2? Okay. I can get it to come up. There we go. Here's x equal 2, and we'll put a vertical asymptote there. I'll put it in red to let you know it can't equal 2. And Justin's here. All right. Anyone else come in since I called roll? Okay, the other. X cannot equal -1. I have a slanting axis there, so I have to slant my asymptote a little bit too, but there's the second vertical asymptote. So we've got the first stages of our graph beginning to take shape. What now? Say again? Horizontal asymptote. What would that be? How do you determine that? A little louder. Okay, ratio of your leading terms. Okay, and what is that ratio of the leading terms? 1 over x. What happens now? The horizontal asymptote is what happens in end behavior. When x gets very large, either positive or negative, what is 1 over x becoming? Closer and closer to 0. Okay, so the horizontal axis, y equals 0, is your horizontal asymptote. I guess I should put, these are the vertical asymptotes. Okay, so your horizontal asymptote is y is equal to 0. So there's the x-axis is a horizontal asymptote, y is equal to 0. There it is. Okay, good, got those done. What else can we glean from this information? Second? X-intercept. What is true about the x-intercept? Okay, the x-intercept, I think I'll go back to dark color now. So the x, I thought I went to dark color. Okay, the x-intercept is where y is equal to 0, but y, of course, is your alpha of x, and what makes that alpha of x equal 0? X equals 0. So that's true at x equals 0. So the x-intercept is 0, x equals 0, and then what's y? 0. Okay, so 0 is 0. That's the x-intercept, and guess what, folks? It's also the y-intercept. Only one x-intercept, because there's only one value of x, makes that numerator 0, and you can only have one y-intercept, even when no, you're in here somewhere. I taught Torellis here. Okay, there he is. All right, good deal. And okay, so your x-intercept sort of hard to see here, and the y-intercept is 0, 0. You don't have to list it but once, but since we mentioned both. All right. Now, that leaves you with a little bit of a dilemma. What do you need to do next? Say again? Plug in some numbers. I would like you to tell me numbers you'd like to plug in. Say again? 1 looks like a good one. That will tell you what's going on between your x and y intercept and your right-hand vertical asymptote. Any others? So again, -1/2. How about it? Okay. negative 1/2, you need to know what's going on between the the left-hand vertical asymptote and the 0. Any others? How about negative 2? You need to know what's happening to the left. And 3, what's happening to the right. So we got to plug in at least 4 numbers to get an idea of where this function's heading in each of those circumstances. So where you want to begin? 1, okay, he liked 1. F of 1 would be what? 1 over 1 minus 1 minus 2. What's that equal to? Negative 1/2. Okay, so x equal 1, your y is negative 1/2. I know where it's going from here. It's got to be going downhill here and approaching your vertical asymptote. Okay, which one you want to look at next? Negative 1/2. So f of negative 1/2 is equal to what? Negative 1/2 over 1/4. Say again? Minus a minus 1/2, which is plus 1/2, which actually is 2/4. Let me just write it that way. Minus, and how many fourths is 2? Huh? 8/4. Minus 8/4. Okay? So that gives us a minus 1/2 over, let's see, negative 5/4, isn't it? Negative 5/4. All right, Amber's back. Okay. Okay, I think that's the 2. Oh, that's the line there. Yeah, it's it was negative or minus 1/2. So that's the 2 right there. My line is messy. So let me see if I can clear that up a little bit. Okay. Okay. And then I almost lost my minus sign, but you get plus 3/4 minus 8/4 minus 5/4. Okay. So here we see, and who cares what the value is really? All we're interested in is whether it's positive or negative. It's positive, but we will mess with the value. That would be 2 and the 4 would be 2, and that would be 2/5. So 2/5 is just under 1/2. Oh, just under 1/2 here. So there it is. So yeah, we know where it's going here, coming down from here and joining there. So we've got the in between the asymptotes. We need to go right and left of the asymptote. So where do you want to go next? Negative 2. So let's do, I think I'll do it up here. F of negative 2 will be what? Negative 2 over 4 plus 2 minus 2. Well, I can do the plus 2 minus 2. They add to 0, and this gives us a negative 1/2. So here we're down at negative 1/2 again. Well, I think I know where this is going. Has to be approaching the horizontal asymptote to the left and the vertical asymptote to the right. Got it. One more. 3. Let's do it over here, I guess. F of 3. What would that be? 3 over 9 minus 3 minus 2. And again, really all we're interested in really is the sign. And what is the sign of this? It'll be 3 is positive 3 over 4, 3/4. So when this is x equal 3, this is 3/4, which would be somewhere up about there. And that tells us enough. We know you have to approach a vertical asymptote on that side and the horizontal asymptote there. There we have it. Let's see how the book did. Look at that. Theirs looks almost as pretty as ours, doesn't it? Not quite. Okay. They did points. They chose some different points, I think. They used -3 rather than -2. Why would they? But they did. And they used, yeah, the others were pretty much what we did. All right, good deal. Any questions on that? Good kind of problem. Y'all handled it really well. Found your vertical asymptote. Doesn't matter what order you do this. You found your vertical asymptote first. Asymptotes, 2 of those. You plotted those. Then you did your horizontal asymptote from ratio of leading terms and plotted that one. Then you went to find your 2 intercepts. You found out they were the same intercept. You only had one x. It happened also to be the y. So that gave you extra points that you had to investigate, and choosing -2, -1/2, +1, and +3 gave you the other 4 points you needed to identify what the activity of the graph was outside the vertical asymptote, between the vertical asymptote and the 0, between the 0 and the next vertical asymptote, and outside the last vertical asymptote. The combination of vertical asymptotes and x intercepts give you the regions that you have to investigate for your activity there. Now, if we would have had some other points in there, as in extra horizontal asymptote, x-intercepts, or a separate y-intercept, that would probably have eliminated some of the points that you would have to test. But test as many as you need to determine the activity. Any questions on that? Okay, as I said, there is a checkpoint. Well worth your effort to do that checkpoint. All right. Any questions before I erase it? Y'all did well. Let's do example 6. They don't have this one on the slide set either. So let's do example 6. Sketch the graph of f of x is equal to x squared minus 9 in the numerator, and in the denominator x squared minus 2x minus 3. All right. What's the first thing you're going to do before you start sketching the graph? Okay, say that again. Okay, find all the stuff we just found for the last. Okay, yeah, I thought that's what you said. Okay, all right. And here's generally the way to begin, because you're going to have to do it anyway. Factor everything in sight, okay? The last one, only the denominator could be factored. Here the numerator and the denominator look like they could be, so factor everything first. That will lead you to the stuff we were looking for and looked at last time. So how does that numerator factor? X plus 3 times x minus 3. How about that denominator? X minus 3 and x plus 1. Okay, if you don't see that, unfoil it, do whatever it takes, check it by x squared plus x minus 3x would be minus 2x minus 3. Yes, that works. What do you notice now? Okay, there is a common factor. You need to get rid of those. But you also have to remember that x cannot equal 3. Even though you canceled out those, or factored them out, divided them out, you still have to recognize it can't equal 3. And why can I not? There you are, Ryan. Okay. And I'll say it again. I've said it several times, but congratulations for those of you who were recognized at Honors and Awards. That was pretty nice to see all my students there. Okay, good deal. Okay. Now, remember x can't equal 3. That sort of simplifies our problem, though. What do we come up with now? Say again? Okay, yeah. Your vertical asymptote says, and I think I'll put this in red, the vertical asymptote from here, x cannot equal -1. Okay? Anything else? Say again? Okay, y-intercept. Okay, we'll do that one. Tell me what to do on y-intercept. Put a 0 in for x. So x equals 0. And what would the y be then? 3. Y equal 3. So there's your y-intercept, 0, 3. Perfect. Okay. Next, x-intercept. Okay. Okay, the y is your f of x. That's your y, remember. And the only way this can be 0 is if that numerator is 0. What would make the numerator 0? X equal -3. So this is y equals 0, and that gives you x equal -3. So your x-intercept is -3, 0. Okay? We got 3 out of the 4 keys here. Horizontal asymptote, how do we do that one? Say again? Ratio of leading terms, if I can ever get the red to come up. Ah, maybe it did, yes. Ratio of leading terms, we'll take the reduced ratio of leading terms, though you could have taken this one too. It works. And what is that? Okay, so your horizontal asymptote is y is equal to 1. Perfect. Now we can start our graphing. So let's go back to a dark color and do our graph somewhatly here. Tick off some points. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. -1, 2, 3, 4, 5, 6, 7. Positive 1, 2, 3, 4, 5, 6, 7, 8. -1, 2, 3, 4, 5. Okay. What you want to do first? Okay, vertical and horizontal asymptotes. So I think I'll go back to red then. Okay. And what you want to do first? Horizontal first, and that's where y is equal to 1. You go up, y is equal to 1, and then do a horizontal line through there. Now we do it in red just because we do the vertical in red. Remember, the function can touch or cross a horizontal asymptote. It can't touch or cross a vertical asymptote. Okay? Next. X equal -1. That to the left here, there's your vertical asymptote. And that one, it can't touch or cross. So that splits our graph into 4 sectors, okay? So we know the graph has to be somewhere in there. Next. Okay, that is a hole in the graph. Okay, remember that. It's a hole in the graph. So since you said that, I'm going to put, this isn't where the graph is, but I'm going to remind myself there's a hole there by putting a circle around 3. Okay, but that's not on the graph necessarily. Okay, but good to remember that. Next. Second. And which one you want to do first? Y-intercept, and how do you do it? 0, 3. X0 up 3, okay? There's your y-intercept, okay? I know right now where the function is in that quadrant. It has to approach the vertical asymptote from this side and the horizontal asymptote from this side. Got it done just with that one point. Next. -3, 0. -3, 0. Right there. Okay? I know exactly where it has to be now. Approach the horizontal asymptote this way and the vertical asymptote that way. Now, what I did leave off was this. I have to have a hole in the graph at x equals 3. That's how you do x can't equal 3. That's the hole in the graph because that's a common factor. A little bizarre, but true. Okay? Does that make sense? Well done. Okay? Sure helps a lot when you can cancel something out. Common factors, it simplifies a lot. And they did a lot more points than I did. Our two intercepts, horizontal intercept and vertical, x-intercept and y-intercept, they basically define where the graph has to be there, except for x can't equal 3, so you have to remember to put the hole there. Good deal. Any questions on that? All right. That is example 6, and there is a checkpoint. I would highly recommend that you take a look at the checkpoint too. All right. Now, the next portion of this section we're going to skip, but I will at least familiarize you with you. This was example 3 here, so we're going to move past that. Okay. Slant asymptotes. Okay. Now, what this is a real special case of what we have talked about before. Consider a rational function whose denominator is of degree 1 or greater. Okay, so you have to have something in the denominator with a variable in it. Okay, not just a number. Okay, a degree 1 or greater. If the degree of the numerator is exactly one more, and only one more, than the degree of the denominator, then the function has a slant or oblique asymptote. Okay? Here's the example. Now, what we would have done before, we would have looked at this and said, ratio of leading terms. Yeah, x over 1, so when x is very large, you're going very large. You would have said no horizontal asymptote. But because this numerator is exactly one more, it is an x, okay? It could have been 3x or 7x or minus 4x or whatever, but it's exactly 1 degree more than that. That means we have a slant asymptote, okay? Now, they haven't shown you how to do that yet. They've drawn it, but they didn't tell you how they got it. Guess how they do it? Divide. Divide this into that and see what you get. Okay? And that's hopefully what they will do next by dividing x plus 1 into x squared minus 1. What you have is x minus 2. They haven't done the division, but you know how to do that. Actually, this one you could use synthetic division. You can't always, but if this is x cubed minus x and this was x squared plus 1, then you still do division, but there you have to do long division. But you wind up with this plus a remainder. Okay? This gives you your slant asymptote. Y is equal to x minus 2. Well, that is, let's go back here and look. You see your y-intercept is -2, and your slope is 1. So there's your slant asymptote, or oblique asymptote. So some that don't have a horizontal asymptote, if that degree is exactly 1 more in the numerator than the denominator, it will have a slant or oblique asymptote. But we're not going to. The rest of it, x can't equal -1. Everything else is the same. X and y intercept, everything else is the same. But once you get the slant asymptote, your x and y intercept are going to identify where you are here, so you know where you are in that part. You'll have to do a sample test point here to get you there. But don't sweat it. You're not going to be tested on that. Nothing in your, well, frankly, I just don't find a lot of use for this. You know, it is interesting. You can, you certainly is another useful tool, but I sort of think, so what? Okay, so we're not going to do this any more than what I just showed you. See it? If you ever need it, at least you've been exposed to it. Okay? So this is, will that qualify? Yeah, that would have a slant asymptote. We're not going to do it. Just do your division. You'll get it knocked. Okay? Oh, actually, yeah, it would. Okay, you go through and do all the other things, x-intercept, y-intercept, all those things, you do the same. Vertical asymptote, it's just that you have a slant asymptote with y is equal to x for this one, and you do additional points, which you may or may not need to do, and that's what you get from this one. Okay? Again, you're not responsible for it, but don't sweat it. But you see your vertical asymptote comes from this, x can't equal 1, there it is. Your slant asymptote, when you did your division, you get y is equal to x. And then you have a remainder. Who cares about the remainder? That means your intercept is here. That's your identity function. Slope of 1. Don't always have a slope of 1, but you do. And you did have a y-intercept here, x-intercept here. Well, that gives you this side you need to do over here. It's conceivable, but seldom the case, that it would be up here. So you just do one test point here that shows x equal 2. Oh, no. You had an x-intercept here, y-intercept there. You knew all the points. You didn't even need to do any test points. They did a couple extra work, okay? You knew it had to be between those things. All right. Now let's do some applications. We do want to do these, okay? There are many examples of asymptotic behavior in real life, okay? For instance, example 8 gives you one. Oh, here, I was reading that. For instance, example 8 shows the vertical asymptotes can help you analyze the cost of removing pollutants from smokestack emissions. Didn't know that, did you? Which almost it sort of did remind me, I don't know if any of you are aware of it, but this Saturday, coming Saturday, there is a science march at Lynn Park in downtown Birmingham, and it should be a really nice thing. I think it goes from maybe 9 or 10 in the morning until maybe 2 in the afternoon or something like that. I think there'll be food trucks. My wife's a member of 500 Women Scientists, and they'll have a table there. So I'll be there. Our dog will be there. It should be a really fun time. So if any of you want to come out and participate, it should be fun. All right. Just the thought of, this. Utility company burns coal to generate electricity. Yep. Happens more in the U.S. than any other form. Okay. Though we're moving away from it. The cost C in dollars of removing P percentage of the smokestack pollutants is given by this. C is equal to 80,000 P. Now, P is a percentage here. I guess it is a percentage then. I would have guessed it would be a decimal number, but they're saying it is a percentage. Divided by 100 minus P. Okay. Now, obviously, do you think you can remove all the pollutants? No, never going to happen. And that would be 100% removal. That would give you 100 minus 100. Not going to happen, okay? Because the more you take out, the greater the cost is going to be. So you're a member of the state legislature. Oh, sorry about that. I'm sorry, okay. Considering a law that would require utility companies to remove 90% of the pollutants from the smokestack emissions. The current law requires 85% removal. How much additional cost would the utility company incur as a result of the new law? Okay? So, actually, you don't have to do a graph on this. You can just plug them in. That's all you have to do is plug in a 90 here and a 90 there, calculate the cost. Plug in an 85 here and an 85 there, calculate the cost. That would be, the difference would be how much additional cost. Now, I think what they're going to do is actually do the graph of it. Surprise, surprise, this book would do a graph. Can you believe it? Okay. But let's see how that goes. You want to just plug and chug and see what you get? Okay. Let's do C of 90. That would be 80,000 times 90. See, your numerator gets bigger, over 100 minus 90. Your denominator gets smaller. It's going to make for a big increase in cost. So this will be 7200000. Okay? I think I've got the right number of zeros there. Yep. Divided by 10. I'll wipe out one of those zeros. That gives us a cost of $720,000. Not too hard to do, is it? Okay. 85 is going to be a little more because I can't do it in my head, but let's try it. C of 85%, the current law, is going to be 80,000 times 85, because that is a percent, divided by 100 minus 85. Okay, let's see if I can do that one in my head. It's going to be a 0, 0, 0, 0. I got the 4 zeros done. Another 0 for my 40, and then 64, 68. Okay, so you see the numerator did drop. Your denominator went down to 15. And now I'll ask somebody to please use a calculator. I'm tired of doing this in my head. What would be the cost here? A little louder. 433,000? Huh? 53,000. 333. I thought that might be coming. And 33 cents. Okay. Okay. I bet. Never mind. All right. Look at that. Not quite a doubling, but awfully close to it. To get that extra 5% reduction, it's going to cost you almost twice as much as it did to get the 85% reduction. Not quite. This is where you reach the point of saying the law of limiting return, diminishing returns. Okay? Yeah, you can get it made out. You might have the technology for it. Sometimes you don't even have the technology for it, and then it might be really expensive. But this time you do, but it's just going to cost so much more. Now, this is getting into maybe politics or something, but when would you want to do that? What would justify that? If that extra amount of pollution you were allowing in the atmosphere was causing a lot more asthma or other breathing difficulties or illnesses and things like this, and it was costing the population, then it might be worth it. Okay? So you just have to weigh the consequences. You're paying one way or paying the other, which way? And if you can minimize human suffering, that's a big deal too, okay? But if it's not going to make a lot of difference there, you might say, no, we can live with the 85, okay? Tough choices, always tough choices. Okay, now, that was a straightforward way to do it. And I think that's what the book did too. Yeah, they did it exactly that way. $453,333 is the current cost to get it up to 90, 720,000. Yeah, they did it just like we did. And the new law would require the utility company to spend an additional 266,000. So I was a little off. Yeah, I said almost twice. It's not quite. Half as much again, approximately. $266,667. Okay. Yeah, they're showing the same thing we did. There's the current cost. There's the 90%, what it would cost. Gave you a difference of $266,667. Oh, and they didn't even do the graph. Oh, thank you very much. So, but that is an example of a rational function. Okay, checkpoint. They have one there, well worth your time. Here's another one. This isn't on your slide set, so let's see. Where's going to be? Let's do it here. Okay. Example 9. Find a minimum area. A rectangular page contains 48 square inches of print. Okay? They show it in landscape mode. Okay? 48 square inches of print. The margins at the top and bottom of the page are each 1 inch deep. Pretty ugly picture here, but you get the general idea. Okay? Oops, I did it wrong. Margins top and bottom are 1 inch. Margins on the side are 1.5 inch deep. So this is 1.5 inch, and this is 1 inch. 1 inch and 1.5 inch. Okay. What should the dimensions of the page be so that the least amount of paper is used? Okay. What should the dimensions of the page be so that the least amount of paper is used? Okay. Now, the first statement, rectangular page contains 48 square inches of print. That, to me, says this is your 48 square inches. That part that's in the middle, that's your print. They give you what the margins are fixed to be, and they say, what should the dimensions of the page be so that the least amount of paper is used? Okay? Now, how would you begin? Do what? You don't even make it? Okay. You don't print it. Okay. Okay, not acceptable. You want 48 square inches of print. Okay. That's what you want. You want to have that. Okay. Now, what is the question? What should be the dimensions of the page? Right? So, we need to identify some dimensions of the page, right? Let's name something. What you want to call it? Okay, right here you want to call that the height, and this is the width. That'll be fine. I think I'd have gone length and width, but height and width is fine. Just identify what you got, okay? So that's your W, and that's your H, okay? Now, the 1.5 is not, but this is your H. Okay. All right. And you want to find those. Now, what is the dimensions of your printed area? That 4,800, the 48 square inches. We know it's that. But what is the dimensions of that? What would this length here be? It would be W minus 3, exactly, because you have 1.5 inches off here and 1.5 inches off there. How about your vertical? That would be H minus 2. And guess what? That product is going to give you your 48 inches, right? So W minus 3 times H minus 2 is equal to 48 square inches. That's the equation you're dealing with. Okay? Now, you got two variables, though. That's awkward. Okay? Say again? Okay. No, because there's no zero. 48 product principle rule. That only works for 0. Okay? Good idea, but it only works for 0. What you can do here, though, is use this and solve for one of the two. Which one you want to solve for? H or W? W, okay. So I have W minus 3 equal 48 over H minus 2, right? Add 3 to both sides, and now you have W is equal to 48 over H minus 2 plus 3, okay? Now, you can leave it like that, or you can fiddle with it some. This is a rather messy problem, and what you want to do is the least amount of paper, so you want to minimize that product, okay, but it has to still be 48. You know, this is taking too long. I'll tell you this, you're not going to have one like it on the test, so yeah. Now, let's see. They've done it slightly differently, but, you know, we can still handle it. Okay. I think what they do is let's put this over H minus 2 as well. Okay. And what you have then is 48 plus 3H minus 6 over H minus 2, and this would be 42 plus 3H over H minus 2. Okay. Now, that's your width. Okay. Your height is H. So this times this is the thing that we want to minimize. Okay. And basically you have there an equation, you have a vertical asymptote. I mean, you can go from there and find where your minimum is going to be. What they suggest is use a graphing calculator. I was thinking they're going to do it analytically. It's a pretty tough problem. What they're doing is doing a graphing calculator. Plug that into a graphing calculator, see where your minimum value is. And so I'm not going to do any more on this because this is how they're doing it. It's a little cheating, it seems like, but you know, no, it's perfectly fine. And they find the minimum value by using your graphing calculator. I was going to say, when I was doing it, I was setting up and saying, this is beyond the scope of this algebra, but sure enough, that is what we got. And Brianna's here. All right, does anyone else come in since I called roll? So don't worry, you're not going to have one this complicated on your test, okay? But that would be how you would approach it, and without having calculus, you'd have to have a graphing calculator to do it, and that's why I was hesitating and saying, how are they going to get themselves out of this? Well, that's how they did it. Okay, so the book approached it slightly different from me, but it still is no better than what we got. So, so they found the minimum value. Okay. that finishes all we're going to do on this. I'll let you still get that if you want to, but don't worry about it. You're not going to have one. Let's look at the vocabulary under 2.6. Functions of the form f of x equal n of x over d of x, where n of x are polynomials, d of x is a polynomial, d of x is not the zero polynomial. What kind of functions are they called? Rational functions. Okay. Blank, blank, rational function. Number 2, when f of x approaches either plus or minus infinity, so the function, the y value is going to either plus or minus infinity, as x is approaching some value a from the left or the right, x equal a is a blank blank of the graph of f. X equal a would be here, and the function is either going to plus infinity or minus infinity from either side. What is that x equal a called? Vertical asymptote. Perfect. Number 3, when f of x approaches b, as x approaches either positive or negative infinity, y equal b, which is f of x equal b, is a blank blank of the graph of f. Horizontal asymptote. Perfect. Number 4, for the rational function f of x equal n of x over d of x, if the degree of n of x is exactly one more than the degree of d of x, then the graph of f has a blank or oblique blank. Slant or oblique asymptote. Perfect. Homework exercises. Do either 5 or 7 or both. Do any of the odds 9 through 15. Any of the odds 17 through 39. A whole passel of those. I would do all of 41 to 44. The trouble is you only have answers for 41 and 43 in the back, but I would definitely do both of those. I'd do them all, actually. Okay? Do either 45 or 47, or both. I'll let you decide. You don't have to do any of 49 to 61. Those have slant asymptote. Unless you're just interested in doing it, you can go for it. And then graphical analysis. You can do either 63 or 65. Now, I meant to say this earlier, so I'm going to go back a slide, okay, or two. This one, okay. What looks a little different about this function that we did, the cost function? Remember when we did that? They don't have the denominator in degree in decreasing order of the power. So basically what you would do is make this a minus p plus 100. So you have that, and then you do your analysis from there. Unless you look at that and say, well, there's my leading term, so there's what we'll do. So you can rearrange it, or you just notice that even though it's not the first term, it's the leading term. Okay. So just wanted to point that out because I noticed in 65 they don't have it in the right order either. So you just have to acknowledge that or account for it, one or the other. Let's see. I think 67, 69, especially 67 would be a good problem to do. 71 would be a good application problem, but you could do either 71, any of the odds, 71 through 75. You choose. 73 is a lot like the one we just did, so I think you're going to need a graphing utility for the C part there, but you can still work through that. And then true false, you have two true false, 77, 79. At least think through those. And 81, sort of an interesting problem. I think that would be well worth a review of that. All right, we're not going to do 2.7, meaning we are now through with Chapter 2, all we're going to do in Chapter 2, which means the test will be Thursday, and it'll cover 2.1 to 2.3, which you had on your quiz. By the way, you got to turn in the quiz before you can take the test, or you have to ask me to give you a 0 on the quiz. I won't want to, but if you ask me, I can't refuse you probably, really. So turn in your quiz first. those who haven't already. And be ready for the test on Thursday. It'll be a little bit shorter test than the first one was, just because we don't have as much time in the term left for people to wrap it up. So I hope you'll be able to finish it on Thursday, but if not, you know you'll still be able to work on it some. But you only have one. You do know, right? We have classes this week, and we have classes next week, and then final exams. Yeah.
So next week we're only going over the stuff for the final?
No, well, we always go over stuff for the final.
Well,
we're doing chapter 3. In fact, we're going to start chapter 3. No, this is all we're going to do in chapter 2.
I know.
We're not doing 2-7. But then we're going to start chapter 3 today, right now. And then we'll only get a little bit of chapter 3 done. We'll go to that. All right, so there's now other additional things you can do maybe to help you study for the final. Don't worry about 2.7 at all, okay? On page 190 and 191, there is a chapter summary which lists some of the pretty significant things. Some of this would be really good stuff to have on your formula and equation sheet, I would think. That's where I would start if I were making mine. Section 2.1, 2.2, 2.3, you were quizzed on that. 2.4, 2.5, 2.6, you weren't quizzed on that. You'll also have test questions. Don't worry about 2.7, okay? And in 2.6, don't worry about slant asymptotes or oblique asymptotes. Review exercises. Now, the good news here, even in these review exercises, CalcCheck.com has tutorial help for worked out solutions for the odd number exercises. So I would, if you need refresher on any of these, number 1 would be a good problem. Any of the odds 3 through 7, and number 9. That's in 2.1 and 2.2. 11, either 13 or 15 or both, and either 17 or 19 or both, and then 21. 2.3, 23, 25, and 27 would be good. You may not need them all, but those would be good ones to look at because they have the worked out solutions in CalcCheck.com. 2.4, the stuff you haven't been quizzed on. 29, either 31 or 33 or both. 35 and 37, okay, if you need those. 2.5, 39, 41, and either 43 and 45, okay. 2.6, 47, any of the odds 49 to 55, and then 57. Don't worry about 2.7 at all, okay. And then there's a chapter test, and again, CalcCheck.com has tutorial help and worked out solutions for odd number exercises, but the back of the book has all the answers in the chapter test. So even though you won't have in CalcCheck.com, you can still see all the answers. So any of them, 1 through 16. 17 and 18, we're dealing with inequalities. Okay. Any questions? Chapter 2. All right. If you have them, this is a good time to ask. Now, let's see. All right. We've got about 15 minutes. So let's move on to at least an introduction to chapter 3. All right. Exponential and logarithmic functions. If it'll ever come up. They're coming, I think. Taking a while, but it's getting there, I hope. Here we go. All right. The slideshow from the current slide. Okay. Exponential and logarithmic functions. What in the world do we mean by an exponential function? Anyone have an idea? If you don't, it's okay. But anyone have an idea? We'll hit it real quickly. Log functions, then we'll do after we do exponentials, because it works a lot better that way. And guess what? This book likes the graphs too. Yes, okay. We'll be doing graphs with exponential and logarithmic functions. So our objectives here in 3.1 are to recognize and evaluate exponential functions with a base A. Okay? Graph, guess what? And exponential function and use the one-to-one property. We'll get there. It's not quite the same as the one-to-one. Well, it is very similar. Okay. Recognize, evaluate, and graph exponential functions with base E. Anyone familiar with that? We'll get there. And we'll use exponential functions to model and solve some real-life problems. So let's first figure out what in the world an exponential function is. So far, this text has dealt mainly with algebraic functions, which include polynomial functions and rational functions. Okay? Now, I'm going to point something out to you. In polynomial functions especially, and rational functions is the ratios of polynomials, you got them there too, your variable was usually your base, and your exponent was usually numbers, right? X squared, x fifth, 2x, yeah. So that was what your standard mode was. In this chapter, we'll study two types of non-algebraic functions, exponential functions and logarithmic functions. Don't worry about logs yet, we'll get there. These functions are examples of what they call transcendental functions. You meditate on that or something else. Okay. The definition of exponential function. Now remember, for a polynomial, the variable was the base and the exponent was always a number. Always. Okay? Exponential function, your base is a number and your variable is the exponent. So it's kind of the reverse of that. An exponential function of f with base a can be any number going, any number. It doesn't have to be an integer, it doesn't have to be a rational number, it doesn't have to be a positive number, any number is denoted, well, let's see, it does have to be positive. Okay, we'll do that. And it can't be 1. Okay, so positive but not 1. But it could be any fraction, decimal, greater than 0, positive number, but the variable is your exponent. X is any real number. Okay? A is any number greater than 0, not 1. And because you see, if this was 1 to the x, that's always 1. Okay? It doesn't really matter what you're doing to it. It's always 1. So we don't do 1. But we don't do negatives either, because some exponents you can't take with negative numbers. That would get you into complex numbers. So we're not going there. So we keep a positive and x any real number. And a, of course, not 1. Okay, so that's what we mean by an exponential function. So the base a equal 1 is included because anything to the 1 raised to any power is going to be 1. So that's just a very non-interesting function. That's a constant function, not an exponential function. You have evaluated a to the x for integers and rational values of x. Okay? For example, you know that 4 cubed is 64. Of course you knew that. And 4 to the 1/2, that's the square root of 4, is 2. Okay? I think it'd be plus or minus 2, but okay. However, to evaluate 4 to the x, for any real number x, you need to be able to interpret forms with irrational exponents. This x can be any real number. It can be positive, negative, fractions, decimal, rational, or irrational. Now, we're not doing complex exponents. You could, but we're not doing it. We're not doing it. So we're only going through irrationals. Okay. So for the purpose of this text, it's sufficient to think of a to the square root of 2. Yeah, what in the world is that? Where square root of 2 is an irrational number. You can approximate that to 1, 2, 3, 4, 5, 6, 7, 8 decimal points with 9 significant digits, if you wanted to, and think of that as what that would be. As a number that has successively closer approximations, you can do a to the 1.4. That's something you can do on your calculator. A to the 1.4 1.414, 1.4142, 1.41421, and you can just keep on going and get closer and closer, and soon you're as close as you can get on your calculator anyway. But your calculator will also do this, a to the square root of 2. You can do that on the calculator as well. It's doing that approximation for you, and it gets as close as you need to get. Okay? That's what we mean by an exponential function. Your base is a number, and your exponent is the variable, and it could even be an irrational variable. Okay. So, if you've got a calculator, if you don't, please get your calculator and know your calculator before you come in, even for the next test on Thursday, but certainly before you do the one that we're going to have in chapter 3. Okay? Now, here's what my guess is on 3. However much we get covered in 3 next week, today and next week, that's going to be, it's almost going to be like a quiz, but I'll let it count as a test. And then your final exam is going to be short. So your final exam is going to be in 2 parts. Chapter 3 test, very short, and then the comprehensive test, pretty short. Okay. I believe it's Tuesday of finals week. I'm not sure, but I believe it is. Yeah, exactly. What's that? Yeah, we're going to have class today, the test on Thursday, and then class Tuesday and Thursday of next week, and then we'll have the final the Tuesday after that. Yeah. So, you evaluate this, okay? F of x is 2 to the x when x is equal to negative 3.1, okay? Now, how many got calculators? Not that many, huh? Okay. What you would enter here is 2, and then most calculators, this won't be all, but most of them would be this, okay? 2, and there's a key that looks like that. It's a caret key, they call it, and then you follow that by your negation key. Okay, that's not the subtraction key. It's got a parentheses around the minus sign, 3.1, and then you press equal. That's going to be it on most calculators. Any of you got a calculator today? Do you find those keys on yours? Second? Okay. Okay. Some of the older calculators, they don't have this key. They have a key that says a to the b or x to the y or something like that. And in that case, you'd press the 2 first, then you would press, instead of this key, you would press that key, one of those 2. And then some calculators don't have the minus in parentheses. Okay, I'm sorry about this. Then, if you don't, you will see a key that says something like this, plus, minus. Or the oldest calculator, CHS. That means change sign. With those keys, you usually enter the number first, and then you press the key. Okay? If you have the newer calculator with this key on it, you press that first, and then the 3.1. So please know your calculator. If you don't know it, see me before test day comes, and learn how to use it. There's different syntaxes for different calculators, and I can't teach them all because I don't know them all. I don't know which one you got. But that's usually the one you use. 2 caret negative 3.1. But remember that's the negative in parentheses, not just the empty minus key. You have a plus, minus, times, and division. That's not the key you use. It's the one in parentheses, which is the sign key. Okay? In this one, you would be 2 caret, and then again you hit the minus sign key, and then you do the pi. And most calculators, I think, have the pi key. Okay? If you don't have a pi key, then you can do 3.14 or something like that. But most calculators will have a pi key. Okay? That's an irrational number. You're just doing what we were talking about before. On this one, yes, you can have a decimal number here. You don't have to have an integer. 0.6 caret, and then I would open parentheses, 3 divided by 2, close parentheses. But since you know what 3.2 is, you could do 0.6 caret 1.5. That would work just as well. So get used to what you do evaluating exponential functions. Your base is a number, your variable is your exponent. Okay? And here they show you, and they use those same keys I was doing, that f of negative 3.1 would be 2 of negative 3.1, the 2 caret negation key 3.1 enter, and you get 0.116, blah, blah, blah. Okay? Now you might say, why is that a small number like that? Because your exponent is a negative. So this is, yes, exactly. That'd be the same as 1 over 2 to the 3.1. You're absolutely right, which would be 1 over something greater than 8. And sure enough, that's that. Okay, the next one, your 2 caret negation key from here, and then find the pi key, get enter. And again, you got a negative number. That's not far from that one, is it? Pi is 3.14. This is 3.1. So this is a little bit less than that one. That makes sense. And then this one is 0.6. So you're starting with a really small number, but raising it to a positive, an exponent greater than 1. So you get a little bit greater number there. The thing is, you had just a small number to begin with, even though you're squaring it. More, not quite squaring it, but you're getting a bigger number. So it's 0.6 caret, and what I said, open parentheses, 3 divided by 2, close parentheses, or you could have done 0.6 caret 1.5, because you can just do that in your head, and that gives you the same answer.
Our calculator has a fraction function. Can we just?
Yeah, if you have that, you certainly can use that, for sure. And a lot of new calculators have that. Mine doesn't. I have a very old calculator. That's why I didn't think of it. All right, that was example 1. Next time we'll start with graphs of exponential functions, which I know you'll love. Now that will be next Tuesday. On Thursday, we will have the test. I will try to answer any questions you have for the first few minutes, but try to come in ready to take the test. If you run into questions, try to see me between now and then to get those questions clear. Okay? Good deal. What's that? Oh yeah, you can always have a formula and equation sheet. Absolutely. That's why I said back on that summary, those would be good things to put on it. Yeah.
Do you have a copy of that scholarship for the first year student, 3,300 for the 50%, or was that in the financial aid office?
That was in financial aid office, but that deadline was yesterday. Yeah. Sorry, but I mean, go check with them. Maybe they'll take it today. Yeah. Yeah, I ran out. I passed out all mine earlier.
Number 4.
Yeah.
Is it the?
Yeah, use this formula.
Okay.
Yeah,
Okay,
yeah,
got
sorry. I meant to do that and I forgot. Yeah. Okay. Good deal.